electric potential and capacitance. So whenever we have two charges here, one charge and another charge present close to each other, there is some kind of interaction energy that is happening here. For example, if you try to bring this charge close to this point, more close to, if you try to bring Q2 towards Q1, both being positive, it will become difficult for you to bring it more close to Q1, because more close you bring it will become hard. They are going to repel each other, and as they are repelling each other, so their energy is increasing. How can you say energy is increasing? Once you release it, you will see charge Q2 will move right, will accelerate towards the right. That means if you take it towards the left, towards the two charge, if you try to bring it close together, the energy of the system is increasing, because when you release the force, it moves away and it accelerates. This energy, what it is increasing, is called the electrostatic potential energy. We will come to that. Now, electrostatic potential energy, before I go to electrostatic potential energy, we need to learn one more topic here called electric potential. What is electric potential? Means capability. What is electric potential? So electric potential we denote it by V, as you have learned that electric potential V is defined as work done per unit charge. What does this mean? Imagine I have these two charges. I am bringing, this is some positive charge here, some plus charge has been placed here, and I am bringing a small 1 coulomb charge towards this. So I'll have to do some work to bring this 1 coulomb charge towards this. So I have to do 1 times work to take it. So if I bring a 2 coulomb charge towards the same object, then how much amount of work will I have to do now? Definitely I will have to do 2 times of the 1 coulomb charge, 2 times of it. Similarly, if I do 10 times, so like this, you see, every time I bring a charge, my charge, I have to do the sometimes more work I have to do based on how much of charge I am bringing or I am taking close to this plus Q charge. So then instead of expressing the energy, we can only define that what is, how much work are you doing, how much energy are you spending per unit charge, that is this one. So if I am taking a Q naught charge now, so I know this much work is being done, so what is the work done per unit charge I am doing? That is the potential. So if I know the potential, I can easily multiply V into Q, will give me the energy required. So hence this is the most fundamental definition of electric potential. It is defined as the ratio of work done per unit charge. What is the SI unit? What do you think its dimension would be? To find the dimension, you just write dimension of work. Work is energy only, m L square T to the power minus 2 divided by coulomb is ampere into time. Then I can write this m L square T to the power minus 3 into per ampere inverse. The SI unit of electric potential is volt. So SI unit is volt. We denote by V. So what is 1 volt? V is said to be 1 volt if W equals to 1 joule and Q equals to 1 coulomb. That means 1 volt is equals to 1 joule per coulomb. So 1 joule of work when you do for 1 coulomb of charge, then the SI unit of electric potential will be 1 volt. That's it. Let us understand this for a point charge. So what is electric potential? So from electric potential we can easily determine the energy for the system. Let us use it for another case. Electric potential at a point. Electric potential at any point. At a point due to a point charge. How can we do it? Let's see. So let's say I have a charge here, a plus Q charge, and this is the we are interested to determine what is the electric potential at that point P, which is at a distance r from the plus Q charge. Definitely it's a plus Q charge. We know it will have an electric field this way. So if you are bringing any charge, Q naught charge, gradually towards plus Q, you will have to do some work against the repulsion, against the electric field of this, against the electric field of plus Q. So this work done gets stored as the potential energy of this Q naught system, as straight as that. So to find the potential from there, what we can do, we know that at P, what is the electric field? E will be 1 by 4 pi epsilon naught Q by R square. This is electric field at P. So for small displacement, I will draw one more diagram here. Let us take it like this way. This is the point P. This is plus Q. We are going to bring this charge. Let's say I am bringing a 1 coulomb charge only, let's say. To bring it, definitely you will be taking it slowly, as slow as possible. So for that, let's say you are bringing it to a distance of r. From where are you bringing? You are bringing it from, let's say you are bringing it from infinity. So you are bringing it from infinity to this point P, which is located at distance r. And let's say at any point you are at a distance x and you are making very small displacement dx, infinitely small displacement towards plus P. You are going towards P very slowly. Then what do you know? We can write the small work done. So when you are taking the charge very slowly, so consider a test charge. A test charge Q naught is brought from infinity, is gradually brought from infinity towards P at a distance r from Q. So an external force, so work has to be done. Work is done against the electric field of plus Q, against the electric field of plus Q. So what is that work done? So let dW is the small work done. To displace the charge by a small distance dx. Then what do you think dW will be? Force into displacement, right? Force into displacement. So what is the force? Force and displacement. You are working against the electric field. So you are working against the electric field. Electric field is radially outward. So you are working against the electric field. Electric field is this side. And you are going towards P. So that means it should be, we know force can be written as Q naught into E, force into displacement dx, E dot dx, right? So Q naught E vector dot dx vector, but look closely, electric field is radially outward and you are going this, so that means this must be negative, right? So this one should be minus Q naught E dx dW, or dW by Q naught can be written as minus E dx. Now what is this? So dW by, if dW is the work done, so we can write V equals to, we know W by Q naught, or W can be written as V into Q naught. Now, so for small work done, the potential will also be very small. So we can write this, or potential is for small work, small potential. That means dW can be written as Q naught being constant into dV, right? Implies dV is dW by Q naught. Therefore, in this expression, I can change this expression into dV is equal to minus E dx. So from where are you bringing the charge? You are bringing the charge from infinity, and where are you placing it? You are placing it up to x. You are placing it up to r. Therefore, I can write minus, from infinity I am bringing and I am placing it up to r, E dx. What is the electric field at this point? At any point here, what is the electric field at distance x? Minus infinity to r k q. Whose electric field is this? Is it plus q's electric field by x square dx. Now you know the formula, integration of x to the power n dx is x to the power n plus 1 by n plus 1. This is the formula given. So in this case, I can write here also total potential. This will give me from 0 to V. So this will give me V is equal to minus k q infinity to r x to the power minus 2 dx, which if I do, I am going to get this as minus q minus 1 by x. Therefore, V would be equal to plus kq, because V, so total potential would be from infinity to this will give me the total potential V. So kq. Now the boundary, what will be the boundary? It would be 1 by r minus 1 by infinity. Now infinity, as you know, is explained as 1 by 0. Therefore, V is equal to kq by r, or more properly we can write 1 by 4 pi epsilon naught q by r. V is a scalar function, scalar quantity. So V of x means function Vx at any point x is written as 1 by 4 pi epsilon naught q of x. It is a scalar quantity. Potential is a scalar quantity. Potential is a scalar quantity. And we can define potential now. How did we find potential at a point? So we can define electric potential at a point as the work done to bring a charge from infinity to a point on the electric field of another charge. So it is the work done per unit charge to bring a unit charge from infinity to a point on the electric field of another charge. That way also we can define electric potential.